Thank you, Walter. So I'm really pleased and honored to be here tonight as part of the LPI 50th anniversary speaker series, and you know the idea that LPI spent 50 years exploring the solar system. I thought that was really impressive. But then I thought, well, the Earth's part of the solar system, and us geophysicists have been working on it for more than 100 years. So, you know, it's nice, but a little bit late. So I thought that I would start out a little bit with a little bit of history. But first, I wanted to talk about the InSight mission a little bit. You may or may not know, the InSight mission is a mission to Mars, but it was actually sold by myself and my colleagues and approved by NASA with the goal of not just exploring Mars, but understanding better how terrestrial planets in general formed and evolved into the bodies we see today. So the goal of the mission is actually pretty focused. It's a very high-minded goal, if you will, but it's to understand the formation and the early evolution processes of the rocky planets, not only in our solar system, but potentially in solar systems around other stars as well. And we're going to do that by investigating the interior of Mars. And I'll talk a little bit more about how we're going to do that later. But there's some, so that's a great goal, but how are we going to do that? So we're actually doing some specific things. We're going to measure some very specific things. We're going to measure things like the thickness of the crust, whether the crust has large-scale layering on a global scale, whether the size of the core and its composition or density, the structure of its mantle, the heat flux of the planet, which is a measure of how much energy is available to drive the geological processes in the planet, and the rate and distribution of seismic activity and cratering. And so these are, in a sense, these are the details of my contract with NASA. InSight was a proposal. It was a competitive proposal, and we were chosen out of almost 30 other planetary proposals back in 2011 and 12. And so one of the things we did was we made a list of the things that we were going to deliver. And most of these things you can see are numbers. I mean, the crustal thickness, that's a number, 35 kilometers, 40 kilometers, whatever. And so we've got 10 requirements that we put in our proposal. That's basically 10 numbers. And so I actually figured out that's roughly $80 million per number. That's the going rate for numbers at NASA today. So just in case you wonder how much a number costs. So InSight's a space mission, but it's also kind of a time machine. So InSight harks back more than 100 years back to terrestrial geophysics at the dawn of the 20th century. To answer some basic questions about a planet. And at that time, of course, we were asking these questions about the Earth. I mean, there weren't always textbooks around that told you how thick the crust was on the Earth. They actually had to write the books. And before they wrote them, they actually had to know what the answers were. And so these were the questions that physicists and scientists in the early 1900s, late 1800s were interested in. And they're very close to the questions that you saw before. So a little bit of history. So 1889, that's just a little bit before the turn of the century, Ernst von Räuber-Paschewitz actually measured the first quake that was identified in a seismogram that wasn't right under your feet. And so he saw this little this blip on his horizontal pendulum. He was actually looking at the deformation of the Earth's surface from other gravitational objects, the moon, other planets. And he saw this signal, and it seemed very odd to him. He didn't know where it came from. And then a few weeks later, he heard about a big earthquake in Tokyo, and he correlated the times, and it was exactly the right time. And so this was the first detection of an earthquake by a seismometer. It's turned out to be a seismometer on Mars. And he's got this kind of funny facial hair thing going on. That's kind of an interesting mustache, but... And so this was kind of the birth of seismology, and pretty soon, about 15 years later, so we had a lot more seismology going on, and we've got the first detection of the Earth's core by Richard Dixon Oldham. He also has more than adequate facial hair here. And so we're starting to understand a little bit about the Earth. A little bit later, we got the thickness of the Earth's crust, still breathing through a considerable amount of hair. And we're starting to really understand, the structure of the interior of the Earth. This is a seismometer that he used. It weighs about almost 2,000 pounds. That would not have fit on my spacecraft. And so these are things that they're all happening very quickly. And we got the Earth's inner core, finally broke the facial hair hold on geophysics here. Inge Lehmann, deduced the presence of an inner core just by looking at seismograms, and actually took us until the 1950s until we were able to directly measure the core. And so this was really a very astute derivation that she made. And finally, by the 1940s, we were starting to get the distribution of seismic activity across the entire Earth by Gutenberg and Richter. And so at that point, sort of the foundations of understanding the Earth and its seismic activity were complete. We hope to do it in somewhat less than 50 years, by the way. So then we can say, okay, so we can also go back about 50 years to the Apollo program. The Apollo program was asking precisely the same set of questions. The thickness of the crust, the existence or the size of a core, what kind of seismic activity does the planet have, and what's its energy budget. And so, oh, by the way, I had this comic book, this very comic book, when I was a kid. I was amazed to find it on the internet. Graphic novels, pa. So the Apollo program was really trying to do exactly the same thing that these scientists did, 50, 70 years earlier on the Earth. And the Apollo had what they called ALSEP, which was the Apollo Lunar Surface Experiments Package, and it consisted of a sort of central, control unit that had the communications with the Earth and a power system. It had a seismometer, which was the sort of the centerpiece of this system. This is back in 1969, 1970, when digital instruments were just starting to be developed. It had a heat flow probe to measure the heat coming out of the moon. Had a magnetometer to measure the magnetic field and its interaction with the solid planet. And it had a laser retroreflector, which used large lasers in the Earth to actually range to the moon and determine the position of the moon in orbit around the Earth, and not only that, but its rotational state to a high degree of accuracy, to a matter of inches. And so this was a experiment in understanding the structure of the moon. And of course, we had our first advanced deployment system here, putting our heat flow probe on the moon. And so this package, which was flown on virtually all the Apollo missions with some puts and takes, is one of the two sort of capstones of our scientific understanding of the moon that was provided by Apollo. The other, of course, being the analysis of the lunar rocks that were brought back and analyzed for their chemistry and isotopic contact. Those two things actually have worked together to sort of kickstart our understanding of planetary formation processes. So today, InSight's asking exactly the same basic questions about Mars, the structure of the interior, because the structure of the interior is actually the fingerprints of the processes that developed it. But in a sense, InSight's even more of a time machine. It's actually going back 4.5 billion years to the beginnings of the solar system to help understand the processes of planetary differentiation and the evolutionary processes that modify these planets. We're really looking at processes that happened in the first few tens of millions of years after the planets formed, which is just a few ticks in the geological clock. So just basically how a terrestrial planet forms. First, it starts forming from the coagulation and clumping of meteoritic material, dust that's orbiting around the sun. As it grows, the interior begins to heat up and eventually melt, and it's heating up both because of the energy of different particles and meteorites impacting into it and imparting their energy, and also because of the decay of radioactive elements that are mixed in with this dust. Stuff happens, and you end up with a planet. Okay, you've got a crust, a mantle, and a core with distinct non-meteoritic mineralogies. And of course, if you go out and pick up a rock anywhere on the Earth and look at the composition of that rock, look at it in just about any sense, it will not look like a meteorite. And yet, everything that formed the Earth started out as a meteoritic material. And so how do we get this planet that has this really diverse suite of rocks and minerals and so forth from this initially homogeneous thing? And the stuff happens. That's where InSight comes in. You know, it's really the transition from a homogeneous ball of, let's face it, kind of boring stuff into a planet where, you know, you have mountains, you have valleys, you have green rocks and red rocks and all kinds of fun stuff. So that's what InSight's all about. So we have the bones of how a planet goes from that homogeneous state to something, and we learned this basically from studying things on the moon. We start out with that bowl, and it starts to melt as it gets hot, okay? And as it melts, things separate. Heavy stuff sinks to the bottom. You start off with your reduced metals that kind of rains down in some sense into the metallic core. As it cools, you start to get the crystallization of some of the materials in there. And generally, those crystallization products are heavier than the melt they start out in, but not always. So when they sink, but as they sink, they're pulling some of the elements out of that molten mix and changing its composition. As you change its composition, it actually starts crystallizing into other things. And in fact, it can actually redissolve some of this stuff as it becomes a different composition, a different temperature and pressure. And if you're mixing this stuff up, some of this green stuff can get reconstituted into this melt and make even different rocks. And so it's a really complex physical chemical system, one that we do not understand very well, and it's very difficult to replicate in the laboratory. Eventually you get light stuff that floats, heavy stuff that sinks, and you end up with a differentiated planet. And it's the details of this process that we would like to understand better. So why is Mars the place to go to understand that? Right now we have a lot of information on two terrestrial planets, the Earth and the Moon. You would think that maybe the Earth would be the place to go since you don't actually have to go. I mean, you're right here, you can study it. But it turns out that a lot of it, if not all of the evidence, the structural evidence of the Earth, has been destroyed. I mean, the Earth is an active planet. We have plate tectonics that has recycled the crustal material, you know, multiple times. We have a mantle which is vigorously convecting. Everything's gotten mixed up. Everything's gotten remelted. So there's really not much of anything left from the initial processes. The Moon, that might be a great place to go as well. It's been much more quiescent. It certainly has not changed a lot since it was formed. But the problem with the Moon is that it really doesn't give us a very good laboratory for testing things that happen in planets. If you go all the way to the core of the Moon, the pressure and temperature conditions there are only maybe a few hundred kilometers, maybe even less, down into the Earth. And so you're really only getting stuff up here. And all the stuff that's happening in here, which is the bulk of the stuff that's happening on the planet, is never happens on the Moon because you just don't have enough size to make it happen. So Mars is large enough to have undergone most of the terrestrial processes, but small enough to have retained evidence of its early activity. And we have several lines of evidence. And so I like to say Mars is not too hot, not too cold, but it's just right. Okay, so it's the Goldilocks planet. So this is a comparison of the internal structures of the planets. We've got lots of numbers on here, the various different parts of the Earth, the interior, different pieces of the mantle, the outer core, inner core, and crust. We have a lot of knowledge about the Moon as well from our measurements. We've got a lot of question marks here, okay? These question marks mean that we really don't know very much at all about the interior of Mars, despite the fact that we've been going there for more than 40 years now. And I actually have a whole talk about why that didn't happen. It's a really an improbable event, but it did happen. So we're finally in a position of taking away some of these question marks, and it actually makes my job easier because when you don't know anything you find out, people will think you're a hero. So this is an artist's rendition of the InSight lander, and it shows the 3 major investigations that we have. It has the seismometer, which is sort of the heart of our mission, a heat flow probe, and a radio science experiment, which is basically a precision tracking. And so these are directly analogous to the experiments that we sent to the moon 50 years ago. Here's the lunar seismometer, this is the lunar heat flow probe, and this is the equivalent of the laser retroreflector that allows us to track the precise position of a point on the surface of Mars, which allows us to actually track its rotation. So the InSight lander is really just a recapitulation of what was already recognized to be a really good idea back in the 60s. So, but in addition to these 3 instruments, I sold this mission as a very focused and simple mission. NASA likes simple. The simpler it is, the fewer things that can go wrong. So I said, we only have 2 instruments. They said, that sounds great. But I didn't tell them about all the other stuff that we had on there that we need to actually support the seismic measurements. So we have a very capable weather station on InSight. We have twins, which are these 2 things here. They measure the wind speed and direction, as well as the atmospheric temperature. We have an extremely sensitive barometer, a pressure sensor that's on the spacecraft. We also have a magnetometer. These are all things that affect our seismic measurements. And so my argument was you have to know these things so that you can remove the noise from the seismic data. And it's actually even has the advantage of being a true argument. That always helps. And in addition, we have this robotic arm to put these things on the surface and some cameras to help us figure out what it was. And so again, with an analogy to Apollo, this is our excuse for an astronaut, and we have this magnetometer here, which is providing some information that, as well as helping the seismic measurement, all these things actually do their own science, which is really cool. Okay, so let me talk about the seismometer a little bit. A seismometer, I'm sure everyone in here has probably seen a seismogram somewhere, and you're measuring, vibrations of the surface. If you're in California, that's not too big a trick. You can feel it with your butt if you're sitting in a chair and your house starts to shake. But it actually becomes trickier if you want to look at earthquakes that are occurring on the other side of the planet. And the reason why you want to look at earthquakes on the other side of the planet is because in order for those waves to get to you, they had to travel deep beneath the Earth to get up to you. And as those waves travel through various different kinds of rocks, go through boundaries, they are affected by those things. It changes the shape of the wiggles. It changes the timing of them. It affects their frequency. It affects their polarization. And all these things are pieces of information that we can use our mathematical physical models to extract. So each of these seismograms you see is actually a package of information that's been pulled up from deep inside the Earth. And so you need something that's very sensitive to measure something that was shaking 7, 8, 10,000 kilometers away. And so a seismometer has to be very sensitive. So this is a little bit difficult to understand, but basically what you have here is, this is sensitivity in acceleration. So this is 10 to the minus 6, so that's 1/1,000,000th up here. This is 1/1,000,000,000th of a meter per second squared down here, and this is 1/10 of a billion. And this is frequency going from 1 cycle per second to 1/10 of a cycle per second, which is the same as 1 cycle every 10 seconds and 1 cycle every 100 seconds. So that's a very slow oscillation. But these long oscillations are the ones that bring up the best energy. The green line here is the quietest place that you ever find on the Earth. So no matter where you go on the Earth, there's a certain amount of residual background shaking. And that shaking comes both from the fact that there are earthquakes popping off all the time. And so as they bounce around, there's kind of a little bit of a reverberation going. But mostly it's from the ocean. So if you go to to Denver, where we put together our spacecraft, and we put a seismometer on the assembly floor in Denver because we wanted to test our seismometer, the first thing you see is the ocean crashing on the beach in California. You can't get away from that no matter where you go on the Earth. If you go in the center of Asia excuse me, you can't get away from this. And so this is sort of the least shaking that you can measure anywhere. And on Mars, we are measuring 300 times better than that. This yellow line is the performance of our seismometer. And just to give you an idea of what this means, I mean, 10 to the minus 10, meters per second squared, that's a small number, but how small is that? Well, let me tell you how small that is. For scale, this area down here gives shaking that's about 2.5 times the diameter of a hydrogen atom, which is a good trick, but over here it's actually more like 1/4 of the hydrogen diameter. So we're measuring motions of the Martian surface smaller than the size of an atom, and we're doing it in the dirt, in the weather, 200 million kilometers away. So I think it's not quite magic, but it's really close. So these seismometers are pretty amazing. So these are our seismometers. We call them VBBs for very broad band. They measure across a very wide frequency range. And they're sitting here on the surface of Mars. So how do you actually allow them to make those measurements? You can imagine if you're measuring vibrations the size of an atom, it turns out everything in the universe affects you. Temperature variations, a little bit of expansion and contraction, boom, that's all over you. If the wind blows, forget about it. A little pressure front going through actually makes the ground go boom and back up again. And so all these things are happening. So what we have to do is isolate that seismometer from everything else. And so what we do is we wrap it in a lot of stuff. Okay, and we isolate. So the first level of isolation is what we call our sphere, and that is evacuated to a hard vacuum. Heat doesn't go through vacuum very well. A lot of things don't go through vacuum, so that's our first line of defense. Then we wrap it in a sort of a thermos bottle, so a double-walled thermos bottle to get another sort of level of thermal protection. And finally, we put a windshield over it, which also keeps some of the temperature off. This is kind of cool because we have a solid dome up here, but we have to be able to put this down in the dirt. And so we have a flexible skirt that goes around it. And finally, on the bottom, we actually have chainmail, and that drapes over the different rocks and actually seals it up against the wind. And it turns out to be extremely effective in doing that. And so this actually allows us to beat down the environmental noise to the point where we can start to see these very small seismic signals. So here we are at Mars. The seismometer is on Mars, almost. So we've gone about 600 million kilometers to get to this point, and yet we're 1 meter short of actually being at our destination. So after those 7 minutes of terror, almost there, but not quite. And you say, well, obviously, you're going to put it on the ground. It's not quite so obvious. So this is a picture Viking took of itself back in 1977. This is actually the seismometer that went on the Viking mission. Okay, this is the ground. These two arrows aren't going to the same place. What's wrong with this picture? Well, it turns out that the reason why I'm talking about going to Mars to measure seismic activity for the first time is because the Viking seismometers really didn't do the job. They were kind of an afterthought on a biologically driven mission, and so it was a sort of a Hail Mary. Maybe if there's big Marsquakes, we'll see them. It really didn't work very well. So, but they did impress on us the importance of actually getting down onto the ground where you can make your measurement. So what I have here is I'm going to have a movie of our SEIS deployment. So this is a frame from our instrument context camera, what we call our ICC. It's a camera that's bolted to the spacecraft, and it's a wide-angle camera. This is not the curvature of the planet. This is a 115-degree field of view, sort of like the backup camera on your car, and it sees the entire space that the robotic arm can reach. So there's kind of a crescent that we can reach with that robotic arm. This shows the whole thing, and so we can kind of take pictures periodically to see our progress. And so I'm going to start this going. We start on Sol 22, so we spent the first 3 weeks taking pictures and figuring out where we're going to put it, and then we start deploying our seismometer. So bing, bang, it goes right down right away. But then we have to start adjusting things. We have to take the grapple off, and this tether has to go down. Boom, boom. So the tether's down. Now we have to figure out how to isolate this tether from the spacecraft. It turns out that this is very good conduit mechanical things. So we take our arm, we have a little loop here, and as this arm comes back, and it's pulling the tether back away from it a little bit. There, you can see it move the first time. Not far enough, let's move it again. Yeah, that's probably good enough. Then we finally come in with our wind and thermal shield, kind of a flying saucer moment there. We put it down, and we're done. And that only took 2 months. So you see, we're at Sol 70 here. We started on Sol 20. It's 50 days. It's really slow motion when you're working on another planet. But there we are afterwards. It turns out that that worked very well. So we were actually able to see our first Marsquake. We announced that a couple of weeks ago. This is the first Marsquake on Mars. This is the actual vibration. We have 2 sets of sensors. We have what we call our short period sensors, which measure high frequencies, and our very broadband sensors, which measure low frequencies, and they have some overlap. This was large enough to be picked up on both of our sensors. It looks pretty much the same. So this is the event. And the way we actually look at this most of the time is in this space, which is what we call a spectrogram, and that's looking at the frequency content as a function of time. And that's how we actually are able to tell when something's a quake and not just the wind blowing. You can see lots of stuff going on. That might be a quake, that might be a quake, but we can look up here and see the very different appearance of this stuff than what's happening here, okay? And so it's not just how big it is, but it's actually how this is distributed across the various different frequencies. And so even though we saw lots of stuff going on every day, all day long, wind blowing, pressure going through, magnetic field varying, everything's happening, we finally it took us 2 months of watching before we saw this very tiny quake. And this is a blow up of that same quake. We don't really know what magnitude it is because it's actually really tiny. You know that the Earth noise I showed you, this would never show up on an Earth seismogram. It would be way down in the noise. We're guessing it's probably somewhere around magnitude 1.5 to 3, most likely in the 2-ish. It might be somewhere between 100 and 1,000 kilometers away. So this is what we think is a comparable event on the Earth at the same scale. This is 1 minute ticks. And so you can see, we're starting up here and we're going off about 10 or 11 minutes before it dies off. The earthquake's done in less than a minute, okay? And that's really different kind of behavior. It's not really what we expected. We expected Mars to act kind of Earth-like. What it does look like is a moonquake. So this is a moonquake. This is 40 minutes now. I put these at the same time scale. You can see we die off a little bit quicker, but it's really reminiscent of a moonquake. So this is already telling us that, contrary to our expectation, at least the outer parts of the Martian crust and this quake probably spent most of its time, these waves probably spent most of their time in the outer few kilometers, few miles of the planet, is more moon-like, which means it's very dry, very heavily fractured. And this is, like I said, contrary to what our geological understanding of the planet has suggested. So we're already starting to rethink some of what we thought we knew about Mars just from this one little tiny quake. What we're really waiting for is a big quake, boom, like a magnitude 4.5. And this shows the waves propagating across the surface. They go past our seismometer here, and you can see over here the seismogram. When you have a quake this big, 4.5 is kind of a moderate-sized quake on the Earth, but on a small planet like Mars, it's a big boomer. It goes all the way around the planet and then keeps on coming back at us from the other side, comes back around and actually hits us a second time. You can see it here hitting us a second time, and then actually even a third time if it's at this size, and another set of waves here. And this is the secret of being able to do seismology on Mars with just one seismometer. If you know anything about seismology, you probably know that you need at least 3 seismometers to do anything, right? And that's something that everybody knows, which is not quite true. And if you have the right kind of signal and the right set of signals, you can actually use this additional information to get the distance and the location of the Marsquake, and we've demonstrated that we can do that using actual seismic events on the Earth. Okay, so let's go to our second instrument. This is the mole. This is something that's designed to actually take the temperature of the planet. It's supposed to go down. So we have a mole, it has a hammer. It's actually something that winds up on a spring, pops down, and knocks it into the ground just a few millimeters at a time, or even a fraction of a millimeter. And then when it rebounds, it's the impulse is absorbed by another set of springs, which actually slows it down and kind of spreads out the force, and it allows it to actually make forward progress by using the friction on the sides to keep it from just popping back up as far as it went down. I stopped the video at this point because on Mars, this is actually where it got stopped. So several months ago, we started this process. We went down about this far. We think we're about 35 centimeters, which is about a foot down, but we have still a few inches sticking out the back. We don't know exactly why that happened. There may be a rock here. It may have actually just kind of wiggled around and made enough of a hole around itself that there's no more friction against the sides and it's popping up and down. But anyway, we're looking at ways to get around that. And if we do, we're going to go down, and every meter or so, we're going to put out a heat pulse, and we watch that heat pulse cool off, and by the speed at which it cools off, that tells us something about how fast this material conducts heat. With that information, we can use the measurement of the increase in temperature as we go down. So it's not going to increase very much, but some of you know if you go down in a mine shaft, it gets warmer and warmer as you get closer to the Earth's core. So we actually have temperature sensors all along this cable, so we can measure the temperature from the cooler areas up here on the surface all the way down. It probably increases something like 1/100 of a degree, but we'll measure that very precisely, and we're actually able to extrapolate that down deep within the planet and understand how much energy is coming up out of the planet, and that energy is actually what drives the geological processes on the planet. And then our third experiment has to do with precision tracking, and we don't actually have any results from this yet either, because we accumulate this information over a long period of time. But what we do is we send radio signals from our deep space network to the spacecraft, and the spacecraft has a radio that as soon as it receives a radio wave, it immediately turns it back around and sends it back to Earth without even interrupting the wave. And by doing that, we can make the precision measurements on the ground on the Earth to figure out the location of that spacecraft in space to an accuracy of better than 10 centimeters. Which is 4 inches, which is not very many inches when you're 60 million kilometers away. I was talking about the seismometer being almost magic. This is as close to magic as I think you can get with science. Being able to actually reliably measure the location of something to that accuracy is mind-boggling to me, and I even kind of know how they do it. But meanwhile, what happens is as a planet is rotating, we're actually tracking that spacecraft, which is rotating with the planet, which means we can figure out where the North Pole is. We can figure out where that rotation pole is. And as that rotation pole wobbles around, that wobble of that pole is a consequence of two things. It's a consequence of the precession of the planet as it kind of wobbles on its axis the way a top does. And that's related to the distribution of mass with the planet. As a figure skater pulls their arms in, they bring the mass in, they spin faster. That's an effective moment of inertia. That tells us something about the size and the weight of the core. But those two things are still sort of convolved together. In order to break that and figure out those two things separately, we look at smaller wobbles of this axis, which happen on kind of a yearly basis, and that's actually due to the sloshing of the liquid core around. So you have the core that kind of sloshes around, and it affects the location that rotation pole in. With those two things, we can actually determine with a very high degree of accuracy the size of the core and the density of the core, and the density is related directly to its composition. So those are our main experiments, but our sort of auxiliary payload is also going to do some great science. We have a weather station on Mars. It's made of a pressure sensor. It's a barometer, but it's an extremely sensitive barometer, hundreds of times more sensitive than what you would normally do for weather stuff on the Earth. And we have some wind sensors. We have one on each side because as the wind goes over the spacecraft, it gets all kinds of turbulence. So we like to pick up the wind from the wind before it hits the spacecraft. So we have one on each side in order to do that. And we are measuring these quantities around the clock every day. And we have this up on our web, so you can actually go and look at the weather on Mars, the latest weather on Mars. So I pulled this down last night. The latest data we have on there is from a couple of days ago. A high, balmy -7 degrees Fahrenheit, and a low of -147. It's an early spring day on Mars. And so actually you can go and check this out yourself anytime you want. And of course, it's great to have a weather report like this, but the real scientific value is in looking at the details of the behavior and starting to understand the processes of atmospheric dynamics on Mars, and then being able to extrapolate that to better understanding what's happening on the Earth. And we're already starting down that path. And finally, of course, we have pictures. Okay, so I'm a geophysicist, which means I like graphs and charts, and I've been on missions all my life that were run by geologists, and geologists love pictures. And so when I helped design my mission, I said, I'm not going to have a camera on my mission. I'm sick of the pictures getting all the glory. But I did finally cave. Cameras are actually useful, it turns out. And so I justified it by saying, well, we need to be able to look at where we're going to put the instruments. And so that was my justification. But actually, we're getting a lot of really cool pictures. This was the first picture that we took when we landed, just a few minutes after we landed on Mars. This kind of famously dirty picture. This is the same picture that you were seeing in the movie of the Seismometer deployment. This is before we took the lens cover off. But so all this dirt is on the lens cover, and then we took the lens cover off, and it really looked just about the same. The lens cover didn't work very well. Turns out that the camera's pointing down here. We have a rocket engine here and a rocket engine here, and everything's getting pushed up. And so the things got in underneath the lens cover. And so we were a little bit disappointed. But so here is a picture today, same camera, and you can see most of that stuff has fallen off. And so we're actually getting really cool pictures out of that camera now. So that's our wide-angle camera, or our backup camera. We also have a medium-resolution camera where we can take pictures of the deck. This is actually looking back underneath the lander. This is a hole we dug with one of our rocket engines. It's about 1.5 feet deep, which is kind of a little bit scary since the foot's right here. But we can take these pictures, stitch them together into mosaics like this one. This is one of our early mosaics. We're actually putting together an even higher resolution mosaic right now in stereo in 2 different directions. And so we're going to have a really fascinating view of this place on Mars. But I have to say that every time I look at this picture and I sit down with the geologists on our team, I just have to smirk, because this is a gloriously boring spot geologically. And so the geologists are trying to eke out something interesting, and they are finding out something interesting. But most Mars missions, they're driven by going to some place that's geologically interesting. So I want to look at the core. Any place you land on the planet, you look at your feet, there's the core, right? So I deliberately picked a boring spot, not just to spite my geological friends, but actually to make the landing a little bit safer. The other thing I'm kind of proud of is this picture here. So this is the calibration target that we put on the deck, and we use a calibration target to balance the colors and to fine-tune the focus and so forth. But I had a little bit of fun with this, and I actually put together a calibration target that includes the flags of all the countries that were participating in this mission. The seismometer was built mostly in Europe, France, Germany, Switzerland, the United Kingdom, with a big contribution from the US. The heat flow probe came from Germany. The wind sensors came from Spain. This is a truly international endeavor, and I think that it really shows that what we can accomplish when we work together. The other cool thing about this picture are these 2 little circles here. These are the names on Mars chips. So I don't know how many people, did anybody in here go to the website and sign up to have your name sent to Mars? Nobody? Oh, okay. So if you look real close, you're one of 2 million names that are engraved with micromachining onto these chips. So a little piece of 2.4 million people are sitting right here on the deck of our spacecraft. And at this point, we have over 2,000 images. as of Sol 158, which was yesterday. And so thank you for your attention, and I hope you all have a good night. And also, you can see the latest pictures and weather. They're all posted as soon as the data hits the ground. If you're up in the middle of the night, you might actually see the stuff before the scientists do. So mars.nasa.gov.insight, go ahead and check it out. Thank you.
Okay, let's start with Q&A. So if you could just remember to wait for us to hand you the mic, it'd be much appreciated. And, okay.
You had a few pictures. Do you have one when the solar panels were cleaned by a little tornado? Because that's us. We lost opportunity recently.
We've had what we consider to be a cleaning event on our dust panels, but whereas when Opportunity got a cleaning event, it would double the power or get most of the dust off. The cleaning event we've seen so far is just a little tiny blip in the solar panel. So we haven't had a good cleaning event. Our panels are getting very dusty, and that was expected and predicted, and they're actually following the curve that we predicted. And so right now we're not quite at our peak power, but we're still getting lots and lots of power. We designed this with solar panels that were large enough that if we never get them cleaned off, we can go about 2.5 or 3 years on Mars before we start having issues with power. Everywhere we've gone on Mars, we have encountered something which we believe is probably dust devils that have cleaned off the solar panels, and so we're confident, I would say, confident that the same thing will happen here, and we're hopeful that we can get a long-term mission out of this the same way that Opportunity and even Spirit. I mean, Spirit did die during a winter half a dozen years ago, but before it expired, it lasted much longer than its design life. So we're hoping for the same kind of outcome.
What type of storms do you expect up there?
The normal Mars storms. so there are a lot of meteorological phenomena on Mars. The most impressive one, of course, are the large dust storms, and these dust storms are such that the dust gets picked up from the surface and injected high into the atmosphere and can block out the sun at the kind of 99% level in the worst case. Contrary to the movie The Martian, you don't really get high winds with a storm like that. We believe probably a lot of that dust is actually injected by individual dust devils and starting to get things stirred up that way. But you do have windstorms as well. You can get gusts up to approaching 100 meters per second. I think that the Vikings saw some things very fast. The highest winds we've seen are about 20 meters per second, which is something like, I don't know, 15 miles an hour or something like that. But most of the time, not so much. So we expect some windstorms. We expect dust devils, and in fact, we see anywhere from a half a dozen to over a dozen dust devils per day not with our cameras, but with our pressure sensor and even our seismometer. Our seismometer can see these dust devils go by. And so at some point, we expect probably one of those will pass over our spacecraft and clean off our solar panels, but we'll have to wait and see.
The device that measures the spin of the planet, do you have any early results? And if not, how much time do you need to learn about the spin of the planet?
We estimated we need something like 8 months of data before we could start making our first findings from that. So that'll probably be kind of midsummer. And that finding actually is not looking at the motion of the pole, it's finding out where the pole is pointing. And we combine that with what happened with the same measurement we did in 1977 with Viking and made a similar measurement. And then again in 1997 with Pathfinder, Mars Pathfinder, made the measurement. And it takes about 160,000 years for it to make a full cycle. So it doesn't go too far 20 years, but it goes enough to be able to measure. And so we'll have like twice as long a baseline, so we'll be able to basically double the precision on the measurement of that precession rate, and that precession rate gives us that moment of inertia. So we think that we'll get that result, which will be significantly better than what we've had before, probably this summer.
You have a mole that's presently lodged against something. The moles that we had before on Beagle 2 had the capability of reversing itself. You have that capability, and what are your plans?
We don't have that capability, and that was deliberate. I mean, and it's deliberate for a couple of different reasons. The first reason is a scientific one, and that is when you have a strong stainless steel cable that goes down from the surface to your mole, it turns out to be a really efficient pipe for heat to go down there, and that would completely, mess up our measurement. So our cable is actually a thin ribbon cable, like is inside your computer. It's relatively flimsy. We've certainly tested it so that it's not going to be broken under these circumstances. But it's thin plastic. It doesn't really conduct electricity, but it's not really strong enough to be able to pull something up. The second reason is that it is just basically what we call a resource constraint, and that is weight, complexity, and cost. So what we did was we said, well, how likely are we to run into a problem like this and need to put it in some other place? And we did a lot of studies. We ran the statistics. We looked at the abundance of rocks, and we calculated a likelihood of getting down to the depth we need of roughly 90%. So, 9 out of 10. And then we back that up by saying that we don't need to do that to have mission success. Okay, so it was considered sort of a secondary experiment. We certainly don't love it any less, but we knew going in that this was, on some level, something that you can't, you can't have for sure. If you had a rock under there that's 10 feet across, that wouldn't even help. So we had to make some trade-offs. This was what we could fit within both of our cost envelope, fit within our mass constraints, and so we made the evaluation that the risk was worth this trade. And if Mars throws a curveball at us, I blame Mars. Are you going to? We will. I mean, there's several things that we're going to try to do. There are things that we can do with the robotic arm that might be able to help us out a little bit, and we're getting ready to try some of those things in our test bed now. If everything that we do at the surface doesn't help, we might as well just turn the hammer on and let it go until it knocks itself to pieces or gets past whatever's hanging it up. So that's sort of our last resort. We'll just turn it on and see what happens.
When you put up the graph of the earthquake on Mars, were you personally surprised that it more resembled an earthquake on the moon rather than on Earth? And does that indicate that maybe the core of Mars is less liquid than we anticipated? Or what were your thoughts on that?
I was a little surprised. I mean, I've thought for quite a while that Mars, with its history of water, we expect we expect the crust to be fractured. There's lots of craters, and so the crust was fractured. But on the Earth, those fractures get healed mostly through hydrothermal action. So they get re-cemented, and they no longer act as a barrier that will reflect waves and send them off in different directions. And so, based on our knowledge of the Mars geologic history, we expected the crust to be more Earth-like in that sense than the Moon. Like I said, it's possible that that Mars quake, the waves spent most of their time in the upper just few miles of the crust, and that might be very desiccated. That might be more fractured, and so there are ways to sort of rescue our tightly held beliefs, but what we're going to do is we're going to see where the data takes us, and if it turns out that the Martian crust is more moon-like, well, that's a really interesting development, and we're going to have to figure out, well, how does that work with the evidence we have of hydrothermal action on Mars? I mean, we see veins, we see evidence of things that happen. So, is there some other mechanism that's causing this fracturing? Is there different layers of the different materials? All that lies in front of us. None of the things that are happening here we think are connected to the core. The core is actually thousands of miles down, and we're looking at, with that quake, we're probably looking at tens of miles at the most. And so we hope to get something that's going to bounce off the core and tell us something about the liquid state of the core, but we're not there yet.
Take one more.
In regards the heat flow probe, it's still investigation why it stopped, right, the mole?
Yeah, there's been a lot of investigation.
Okay, in that regards, how useful and accurate is the data you have from the orbiters, from the Sharab, to foresee any obstacles in the mole? And second question is, how, in looking at what happened to the mole, how valuable is to send a mission just to confirm what we know from orbiters before sending instrumentation? Will that mission have value?
Okay, so Sharad is, as you know, is a ground-penetrating radar instrument that's orbiting around Mars, and it actually looks at rock layering below the surface, which is the kind of thing that we'd like to know about. Unfortunately, the resolution on that is, it can't really see things within about 10 or 15 feet of the surface at least. That gets kind of drowned out by the surface noise and things. And so within the area that we're looking at, Sharad really can't resolve things, and it certainly can't see individual rocks. It sees continuous layering. And so Sharad, we use Sharad data to sort of look at whether there are extensive hard rock layers in this area, because one of the reasons we went here is because we believe that it's fractured and basically dirt and gravel down to 20 or 30 feet, and so we don't think that a hard layer is going to stop us. The problem is, of course, a rock the size of a baseball, if it's in exactly the wrong place, can stop us. And there's really, the only way you can find that is by sending a mole down and running into it, or getting out your shovel and actually digging it up. We thought about all the different kinds of data that we can bring to bear on this, and we looked at the rocks on the surface, and we extrapolated that down to depth, figuring out what the surface density, how that can map into the volume density as you go down. We did simulations of going down into randomly distributed rocks, and how many times that you actually hit a rock and how many times you get down. And that's how we kind of came up with this number of about a 90% probability of making it down about 10 feet, which is sort of our minimum depth to do it. And so it's one of those things that at some level you can make all the calculations that you want, and you can do all the laboratory experiments that you want, but in the end, you really have to go there and do the thing to find out what's there. And sometimes that'll be successful and sometimes it won't. And so you have to be in a situation where you can afford to fail sometimes if you're going to actually do anything that's really difficult.
Let's thank our speaker one more time.